We are going to get things started. Welcome back to the Skills Seminar for the fall term. We have an exciting list of speakers planned for us each Thursday afternoon. So there's a lot of new faces. So I'm Jackie, and I will be running seminar this term alongside Steph and Ashna. So if you have any questions, please feel free to contact one of us. There is an undergrad course and undergraduate students who are joining us every week for the seminar, and we encourage the undergraduate students to participate and ask questions alongside the rest of us. So we're excited to have you. And the last item before we get started with Adam's talk is that we are in search of a very keen volunteer to take over the job of making our weekly coffee. And if you are willing to do this task, Mauricio has very generously said that he will train you on what to do for 2 months. So do we have any volunteers who would like to take on the important task of coffee duty? And if if you feel this would be a good position for you, you can talk to Mauricio after the seminar. But we are looking for somebody to take over this role. Okay, so now on to our seminar this week. So we are joined by Adam Bradshaw, who's going to be talking to us about form and function, statistical shape modeling as a novel approach to ice hockey skate development. Adam is a second-year master's student in the biomedical engineering program here at the University of Waterloo, and he's currently supervised by Dr. Brent Edwards. Before coming to Calgary, he did his Bachelor of Science in Mechanical Engineering at the University of Colorado in Boulder. And he had a position as a biomechanics research engineer at Steedman Philippon Research Institute in Vail, Colorado. So other interesting facts about Adam is that he's generally an outdoorsy guy, and he enjoys running, biking, swimming, camping, and skiing. So we are looking forward to your talk, and thanks for joining us.
Thank you for the introduction. I'm going to go without the microphone. Hopefully that means things are loud enough. We've set up the Zoom call so that I should be able to hear me the whole time as well. But I'd like to start off by thanking all my collaborators on this work, lab mates, and then by noting that this research was partially funded by CCM Hockey. So getting into it, I believe that hockey skates pose a unique design optimization problem. And that's because they need to be optimized for a number of different factors, namely fit, comfort, and performance, with each one interlinked. And you could argue that all athletic footwear needs to optimize for these factors, but the skates need to do one thing that the others don't, which is protect the wearer. And because skates are required to protect the player from errant pucks and skate blades and whatever's happening to this Flames player here, they must be made out of a rigid, stiff, and protective material, which is usually molded nylon or Kevlar or other types of polymers. And as such, they don't conform to the foot as readily as some of our other shoes that we wear, like running shoes, cleats, and so on. And so the fit of these sort of specialty footwear really needs to be dialed in because the form is less forgiving, right? So taking a step back, footwear fit can be defined as the difference between foot shape and footwear shape. And at a basic level, the optimal fit minimizes the difference between the two. So in order to understand fit, first we have to understand foot shape. And there's been many studies that have done this, examining the human foot and its variation across the population by analyzing large data sets of foot anthropometric measures, like width, length, circumference, and more. And differences in foot shape have been found by age, sex, ethnicity, all the other factors you can see here. And one of the most important studies in this sort of realm was conducted by Ales Yurka and co-authors at a 3D scanning company called Volumental. They examined 1.2 million 3D foot scans from around the world. And from those scans, they looked at some specific dimensions in that data set and concluded a few things. Number one, that foot shape differs by region of the world. So you see the three plots here, the different colors on the plot, which you may or may not be able to make out, show different regions of the world, which is kind of a proxy for ethnicity. They also found that foot shape, as defined by these 2D metrics, does not scale consistently by length. And what that means is that the slope of each of these metrics is nonlinear, right? You can see that, especially for the instep height. And that foot shape does not scale isometrically. And what that means is that the slopes of these curves are not the same across all of these metrics. So this is valuable information, but I'll come back to how I think this can be improved upon. On the other side of understanding fit, we need to understand the shape of footwear. And when hockey skate companies make skates, and really this goes for any footwear company making any type of shoes, they use a template foot called a last. And that's what you see on the left-hand side of the screen here. It's kind of like a 3D mold of a foot shape that they build the skate around so they get consistent inner volumes for all their models. And most shoes we buy come in only one width or fit per size. But because of those rigid properties of the skate companies have traditionally sort of attempted to tackle the problem of fitting a wide variety of foot shapes in the population by offering multiple fit options. So you can see here that CCM offers a tapered fit, kind of a narrow fit, a regular fit, and then a wide fit. And you can see on the left-hand side of the screen how those fits are designed around a few specific metrics, namely forefoot and heel width. And you can see that the different fits scale gradually, but mostly linearly, as skate size increases, right? So CCM believe, based on the feedback that they've gotten from their customers and fit testers, that there is room for improvement in how these fits are designed in order to better suit the population. So to get to the bottom of this, Emily Matijevich, who was a former postdoc in the NIG group, brought in some hockey players into the lab, 3D scanned their feet, and asked them to try on skates and choose their preferred fit. Now, one would expect individuals who are wider than average to choose the wide fit and narrower than average to choose the narrow fit, and so on. But in reality, the results look like this. So from here, we can see that simple foot width could not predict skate preference. Emily also captured around 16 other 1 or 2 dimensional metrics of the foot, including all the ones you see here on the screen. And the multi-variable classification model that they built using all of these metrics and any possible combination of them still could not predict preferred fit. So we can see that to understand foot shape and how it plays into footwear fit, we need to go beyond 2D discrete metrics. And I believe that we can take a more holistic look at foot morphology by examining the whole 3D shape using a technique called statistical shape modeling. So if you're not familiar, statistical shape modeling is a technique that's used to understand a collection of geometrically similar 3D shapes by describing their average shape and then principal components of variation. And it's a technique used widely in the medical imaging world. And these models can be applied in a bunch of different ways. Olivia Bruce, who was a previous student in Brent's group, developed a shape model of the tibia-fibula complex with the purpose of creating better and more representative and more accurate bone model reconstructions for musculoskeletal modeling. And then Tao Lu, a previous postdoc in the NIG group, examined the talus bone, which you can see on the right here, and principal components of variation between the sexes. However, there are very limited foot-specific shape models in the literature. So Brian Conrad and co-authors at the University of Denver had about 4,200 foot scans, which is a lot, but it may not be enough to build a stable statistical shape model. They didn't necessarily perform an analysis to see if principal components stabilized as they added more samples, which is a way of understanding whether your model is representative of the population. And also they said their purpose was to inform footwear development, but there was nothing actually published that actually developed footwear from this model. Whether it's maybe behind closed doors, we don't know, but nothing published. And then Bopana and Anderson had a system that they called 4D scanning, which is really cool as well. They continually scanned the foot during barefoot treadmill walking to see how the foot deforms or changes shape during the gait cycle. Unfortunately, they were limited by a pretty small sample size and the ability to only collect part of the foot, kind of the dorsal surface, as you can see on the screen here. So, to my knowledge, there's no published work that uses 3D statistical shape modeling techniques to develop novel footwear solutions. That brings me to the goals of my project. Overall, we're looking to improve the fit, comfort, and performance of hockey skates through the lens of fit first. The first objective is to develop our own statistical shape model of the foot, and then utilize this model to create a new set of footwear fit options or shapes. And then the second objective is then to evaluate these prototype skate fits for comfort, fit, and performance. And sort of for reference, this arrow shows sort of where I am now. Where the first year of my master's has been focused on the objective 1, and the second year will be focused on objective 2. So moving into the first objective, the data set I'm using to build this model was collected in hockey shops around Canada. So I didn't go and take pictures of 20,099 feet. I was given them. They were taken from customers using CCM's 3D scanning tool to recommend skate sizes. So they were sort of crowdsourced. We have almost so close to 21,000 scans across many different lengths, right? And each scan, an example of which you can see here, is about 4,500 points. So next, I'll walk everyone through on a high level sort of what happens to a foot scan as it goes from the hockey shop to our model. Like I said, these scans were collected in hockey equipment shops from real users around the country on an iPad app with a special sort of scanner attachment. And as you can imagine, they end up coming to us in a variety of shapes and sizes. So we kept the right foot and flipped the left foot so that we could compare them all together. Then in order to make these scans usable in our analysis, we have a rigorous sort of processing workflow to get them ready for the statistical shape model. So we filter out bad scans using certain criteria: foot length, foot width, the ankle dorsiflexion angle, the point density, and then other weird artifacts like the pant leg that you can see on the screen here, and then whatever is going on the left side. That was a real scan we got. And then we use a non-rigid registration technique called coherent point drift. It's not important necessarily what that is, but it basically registers a template shape to each individual scan. And that basically helps us define each shape using the same number of points, and defines corresponding points from scan to scan. So for example, the big toe is always point number 1, right? So you can think of scans being mapped in the same way every time. And then we align them in 3D space using a combination of a few shape alignment algorithms, namely one called a generalized Procrustes analysis. So in the end, when all is said and done, our scans are all cut to the same height, represented by the same number of corresponding points, and then aligned in 3D space. Then we combine what we have left into our statistical shape model. And here's what that looks like. When you combine them all into a model using principal component analysis, this is what we get. So here you see the average shape for all 20,999 scans, and then plotted on top is the standard deviation in the normal direction. And you can see here that regions of high deviation show up at the heel and the toes, which makes sense because we have a wide size range, right? So if we build a model using only scans within the same size, we can get some better information. And we see pretty similar patterns across all 3 of these sizes. As we say in our group, it sort of passes the squint test. And from here, we can sort of qualitatively tell where our fits need to be varied to sort of cover the population. But the model itself doesn't necessarily provide those fit options for us without taking an extra step. So if we're going to use this data set to provide a new lineup of skate fits, we need to organize and categorize these scans into multiple groups. And how we've chosen to do this is an unsupervised machine learning algorithm called T-distributed stochastic neighbor embedding, or TSNE, which is what I'll call it for the rest of the day. And it's a dimensionality reduction algorithm, which does exactly as described. It takes a highly dimensional data set and simplifies or reduces it to something more manageable. And in this project, that's important because in this data set, there are effectively 4,500 different ways that the foot shape can vary. So TSNE takes each object and maps it onto a 2-dimensional plane with similar objects modeled by adjacent points and dissimilarity modeled by distant points. So I'll sort of give some examples as to what that might mean. To illustrate how this works, the original authors of this method analyzed a data set of handwritten digits between 0 and 9. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And if you imagine that we get everybody in this room to write down those digits on a sheet of paper, we'll all have slightly different handwriting. The doctors in the room will have the worst, of course. But maybe some people's 1s are a little more slanted than others, or maybe some 5s look like 6s, and so on. We could sort of test to see how well then TSNE works on condensing this relatively complex data set, right, of 6,000 images. So if we map all 6,000 of the images in that data set, we end up with a 2D map that looks like this. And one thing to note is that the units for the X and Y axes here, which you may or may not be able to see that, but it says AU, and that stands for arbitrary units. And this is somewhat common in the machine learning space or the dimensionality reduction space, because you are distilling a high dimensional data set down into 2 dimensions. And the point is sort of that the axes don't really matter, or what the axes are don't matter. What the algorithm does is it just tries to replicate similarity in the original space with proximity in this new space. So points that are closer together on this map ideally represent digit images that look similar in their original form. So if we then go and color code by what we know the original digits were, we could see that TSNE does a pretty impressive job organizing the images by similarity in the original space. So there's some overlap between clusters, like between 4 and 9 down in pink and green here. And you could picture how a 4 and a 9 might look similar, like if you crossed your 4 and had a straight line on your 9. And we can also see that the 6s and 5s were grouped pretty close together, where really the only difference is closing that loop at the base. All that said, how might the foot scan data set look using TSNE? So here's what things look like if we map multiple sizes at once. And each point here represents an individual foot scan. So it's probably about, I would say, this is only part of the data set, about 15,000 foot scans represented on this map here. And each size is represented by a different color. And recognize that size is a discrete metric, sort of a label that we slap on individuals who fall into a specific bracket for a continuous variable, which is foot length, right? So it logically makes sense that we don't necessarily see the same isolated groups that we saw in the other example data set. We sort of see a more continuous spread from 4 to 5 to 6 up to 9. But honestly, this isn't really very helpful as it is. So again, we go size specific. So here's what the TSNE map looks like for the 2,000 or so scans that are in the size 8 data set. And again, each one of the points on this plot here represents a single scan. Now, maybe you're disappointed in this data that it doesn't look like the previous data set, with clearly defined groupings. That would be ideal. But we can still think of this map as if we took all of the 2s from that example data set, those digits, right, and mapped them on their own. So not going to be too different from each other. Honestly, foot shape isn't as diverse as the digits 0 through 9 are. However, knowing that this map shows similar scans as adjacent points on the map, right, and dissimilar scans as distant from each other, we can still work on pulling out some logical groupings from this map. So we apply something called a clustering algorithm. K-means is one of those algorithms. And what it does is it effectively chooses these black triangle centers and iteratively places those to minimize the within cluster sum of square distances from the points that are closest to that triangle to the center, to the triangle. And K here is the number of clusters that you want the algorithm to find. So once we have those clusters, we then take the mean shape of each cluster, and those become the generated fits. So to recap, we map the scans into 2D space, applied a clustering algorithm to form groups, and then took the average shape of each of those groups to get some representative foot shapes, right? So you can see here that when we compare those 3 generated shapes to the single average shape for the whole size 8 data set, this is how they sort of vary from the mean. So we can see on the left, the first fit is about the same as the average shape for the population, except for that ankle dorsiflexion angle. And the second fit has got a larger instep and is slightly wider, right? It's in the yellow kind of orange region there. And the third is a much smaller volume solution, especially in the instep. So this is our method for developing a new set of skate fits, right? Based on the foot scan data set that we have. And it works best when we do it size by size, sort of removing length as a factor. But how do we measure the success of these methods, at least in theory? Well, we divide our data set into a training and validation or test data set, as is pretty common in the machine learning field. So if we have about 2,500 scans, I think this is the sized out 7 data set I was looking at here. Then we get about 2,000 scans in the training data set and 500 scans in the validation data set. And from that training data set, we apply 2 different methods. We apply the one I just described to generate 3 fits, right? And then we apply something very similar where we generate 1 single average shape for the whole population, right? All 2,000 scans. And then we can calculate the difference or deviation between 2 shapes by calculating what's called the Euclidean distance in 3D space between corresponding points on an individual scan and then the fits that we generated, right? So we align them in 3D space, calculate the difference between the shapes. And if we average that across all 4,500 points in the scans, then we end up with a mean deviation that describes the difference between those 2 shapes. And I argue that that mean deviation represents a simple measure of the fit of footwear. The fit of footwear. And now the comparison I've shown here is what would happen if we took the single average foot shape for the population and created a skate out of it. And that's effectively what the footwear industry does. So if we take all of the foot shapes in a separate validation data set and calculate how well the single average fit, and then the 3 generated fits fit the population with the mean deviation, and then average that across all scans in this new validation data set, we can see that the 3 fits improves the mean deviation, right? A lower number is a better fit, reducing by almost 10% for this particular data set from the baseline of that single average fit. So the novelty here, of course, is that we built this massive model of 3D foot shape variation, and then we can successfully categorize and group similar feet and then create footwear shapes that end up fitting our population better than the current methods do. What happens if we change the number of fits we make? What if instead of 3, it's 2 or 4 or so? For different K values, right, and that K means clustering, this is how our TSNE and clustering combination might look on a single size data set. And we can logically assume that the more fits we create, the better our mean deviation ends up being, right? But by how much is the question. What we found is that increasing the number of fit options created results in an improvement in mean deviation scores. So like a reduction in mean deviation. As you can see, the mean deviation sort of decreasing from left to right here as the number of fits increases. But we also saw a pattern of diminishing returns on our theoretical population fit metric. So when we think about the footwear industry, it's not necessarily feasible to manufacture, distribute, and sell 100 different skate fit options for all the different foot shapes we could see. So this data helps us see where that sweet spot might be for skate companies. We see similar success in improving our deviation metric across all sizes, sort of showing that our methods work well regardless of the data set we use. So to sort of summarize, the first objective of my studies in this project was to develop a statistical shape model of the foot and then use it to develop a new set of skate fit shapes. And we've successfully done so, thereby creating what's actually the largest known statistical shape model of the foot by sample size. And we built this novel method of categorizing foot shapes that we think can inform new footwear grading tables and fit options. I do recognize that there are limitations associated with these methods, though. The first being that the current process generates fits on a size by size basis. And every size data set that I have has a different number of samples and a potentially different TSNE map associated with it. Interestingly, Tao, previous postdoc in the NIC group, previously performed a stability analysis to be able to say that it takes about 1,000 scans of a single size to make the model stable. And for most of our sizes, we meet that threshold. And that sort of tells us whether we can well represent a population or not. And then when I look at the fit outputs for each of these size-specific data sets, they follow a very similar pattern of a narrow, regular, and wide fit produced. However, another limitation of this method is that it also treats all points of the foot for the foot scan as equally important. And we know from other research that not all parts of the foot are equally sensitive to pressure and vibration. And it operates also under the assumption that best fit is the minimized difference between foot and footwear shape, which is admittedly a big assumption. For right now, we really don't have anything better. There's also been research that shows that foot shape can change with dynamic loading, both during and after an intense activity. And it's arguable whether all of that is truly foot shape change or simply a change in posture as our foot muscles fatigue. But there's certainly evidence that swelling can cause temporary changes in foot shape, and this model does not account for that. Okay, so that first objective is effectively what I've been working on for the first year of my master's, right? And this second one is now what I'll be working on for the second half, starting now, really. So based on the fit shapes that these methods have created, CCM are currently developing skates that match our suggestions in sizes 6, 8, and 10. And we'll have those skates actually by the end of this month, which is really exciting. We renamed the fits we generated to sort of match the current CCM convention. So we effectively sort of replaced the lasts that they were previously using for these skate fit options with new population-informed 3D shapes. And with these new fits in mind, we go back to our skate optimization problem. And if we want to optimize for fit, comfort, and performance, how can we use this study to sort of find any relationships between the three? So the primary research question of this second objective is, does the quantified best fit match an individual skate preference? But several secondary questions can also stem from it. We ask, does the quantified best fit match the best on-ice performance? Then does somebody's sort of in-store comfort preference match their on-ice comfort preference? I'll get into what that might mean a little bit later. And then does the most comfortable skate also match the best performing skate? Don't really have answers to any of those questions. I'll recruit about 40 participants who are all recreational hockey players up to an elite level, I should say. They need to fit into a size 6, 8, or 10, and they'll just come for a single visit, approximately an hour and a half, 2 hours, and we'll be doing the testing at the Olympic Oval, which is pretty cool. And this is the overall study design. They'll have a general survey. We'll take a 3D foot scan, and then they'll perform a series of skate assessments. In that general survey, we'll get their demographics data, their skating ability levels, and then their current skate preferences. And from the foot scan, we'll obviously get their 3D foot shape. And then they'll go into a series of skate assessments, both on ice and on flat ground, in sort of an in-store environment that might replicate how an individual would go and buy skates in a hockey shop. We have the 3 skate fit conditions that we're testing, and they'll be tested in a randomized order for each participant, and they'll also be blinded as to which fit type is which. And then they'll also have their own skates, which will serve as sort of a reference sensation. And previous research from this building, from the HPL, has shown that this method can improve the reliability of comfort ratings for footwear. It's sort of like cleansing your palate, right, before you try a new dish. And so the skate assessments will be structured like this. First, the individual will cleanse their palate. They'll put on their own pair of skates, walk around and sort of gain that reference feeling, right? Then they'll put on the first test condition, walk around like they're in a store, testing out some skates that they want to buy, and then fill out a survey rating the comfort of the skate overall, and then in specific regions of the foot too. Then they'll jump on the ice, have a brief sort of structured warm-up that involves a variety of skating movements, followed by 2 16-meter sprint trials, and then they'll fill out that survey again for the on-ice comfort. For those sprint tests, they'll basically be a standard sprint from red line to opposite blue line, the timing gate at 6 meters to measure that sort of initial acceleration period. And they'll have some active recovery and rest between the 2 trials. And once they're done, they'll fill out that same comfort survey as before, rating the on-ice comfort of the skate. And previously in our group, we've been able to distinguish between skating ability levels with these types of sprint tests. So we have reason to believe that it might be possible to see changes in performance based on how well a skate fits your foot. Then the individual will repeat the fit assessment again, including that palate cleanse, the control skate try-on for the other 2 skate conditions. And then they will repeat the first or second condition again at the end as a disguised 4th condition. And that's basically a test to help us determine the retest reliability for each individual's comfort ratings. So if they try on the same skate again, how reliable are they at rating it the same way they did the first time? Basically tells us whether we can trust our participants or not. So these are the outcomes we get from each segment of the study. We'll also ask the individual at the end for their final skate preference rankings, right? Which one was 1, 2, and 3? Most to least favorite. And then the goal is to start this in October and then collect the full slate by early next year. So I'm sure I'll be bugging some of you all to participate. How will we know if this study is successful? Well, if we go back to the primary research question, does best fit match skate preference? Then we might look to find results like this. And what we might expect to see in the relationship between our fit metric and real skate preference is shown here. So on the y-axis, we've got mean deviation, or that fit metric that I was describing earlier in the presentation, and then the preference of the individuals on the x-axis. So for the first group on the left, we'd expect that individuals who prefer the tapered fit also have the lowest mean deviation from that skate shape, right? And so on for the regular and wide fits. And if this method could predict fit preference, that would be very, very exciting. That all said, footwear fit preference is complicated, and different studies have shown that it can be a combination of a number of factors, including foot and footwear shape, but also sensitivity at different regions of the foot, padding on the inside of the shoe, breathability of the shoe material, and all that. So I acknowledge the limitations in only focusing on 2 of these factors in this project. But I do believe that if we're able to move the needle just a little bit in the right direction, develop our understanding a little bit more, that we can then develop skates and footwear that are better suited to our bodies and allow us to move in the way that we want to. And perhaps with all this data that we're collecting, this study can help us determine links between fit, comfort, and performance in a way that's never been done before in hockey skates. With that, thanks to everyone at the U of C, CCM, and beyond for their help on this work, to MyTax and CCM for the funding, and to you all for listening.
For the demographics of the scans, like, are they all male athletes or?
The scans were anonymized, so I don't know for sure.
Okay.
Like, there's no data that came in with the scans. It was simply foot shape. But my contacts at CCM tell me that it was probably 95% male. In an ideal world, we know what the sex of the individual was coming in, and we can make sort of male specific skates and then female specific skates. The same sort of modeling approach can be applied to both. And CCM are currently working on that. So this data was collected sort of over a few years. And based on our group's suggestions, they're now collecting sex with the foot scan data. So they're now collecting female specific data. hoping to maybe apply some of this later.
So are you going to be doing all males for your participants then?
I'm leaving it open.
I'm curious about your participants that you're gonna use for study, your last study. Are you gonna target them? And the reason I ask is, what if you get a participant that is kind of straddling 2 or 3 different groups right in the center of your cluster?
I will not be judging their foot shape before they come to me. I could bring in all of you guys, for example, and I don't necessarily care what foot shape is. I'm not looking for individuals who match a specific location on that cluster. In fact, I won't be using that TSNE map at all because the fits are already created. So I will simply be taking the fits that are already created, those foot shape or fit shapes that CCM have now built skates around, and then the foot shape that comes to me from an individual participant and comparing those. I won't be reiterating or remapping that TSNE process again. That's not how I'll be judging that.
I said another question too. So, in conventional hockey skate fitting, because the skates are so rigid.
Yeah.
Don't they like use an oven to kind
Yeah.
of customize the fit to the individual's foot shape?
Yep.
Are you gonna do that now? Like in the different, are they allowed to do that in the conditions that you give them?
The idea that, yes, that exists, and for people who aren't familiar, you can sort of mold a skate. You can heat up a skate and mold it to match your foot shape a little bit better after the fact. CCM's argument for this is they want their skates to fit better out of the box. Right, so we're not going to deform them in any way using this sort of personalized custom fit oven heating method. That is common in ski boots as well. The idea here is, do they fit well out of the box?
I know your data is quite hockey specific. Do you feel like it could be applied to like figure skates or speed skates, or would that sort of render the data not applicable because of the different like blade angles and foot position?
I will say that this data set, like the foot scans, all came from individuals standing on flat ground, right? So it was individuals like, I think there was, barefoot, standing on flat ground, pants rolled up, just even weight across the 2 feet. So they weren't necessarily in a hockey skate. So the foot scans themselves are not hockey specific. That being said, they were individuals coming into a hockey shop to buy hockey skates. That was the reason they got scanned. So it's sort of a hockey specific population in that way. So in that sense, we're designing skates around a hockey specific population. I think if you had a broader data set, like the 1.2 million scan data set that I talked about other authors having, I think you could certainly use that in other types of footwear. I think it's most relevant in rigid footwear like skates or ski boots or hiking boots, figure skates as well, and maybe a little bit less relevant in shoes that are a little more forgiving like sneakers.
I think just one follow the question that we asked. I think you should somehow control the distribution of type of the in the database. For example, those 40 subjects, if you have 10 subjects in maybe the narrow group, and 8 in the and then maybe 2 or 3 in the wide, then the regular access performance of it's not a fair assessment.
Yeah, it would be great to end up with a nice distribution of people who select all 3 of the fits that we've generated, right? Especially because if you remember the TSNE maps, it looked like it wasn't necessarily hard coded to be even distribution between the 3 groups, but it usually worked out that way. That's how the clustering algorithm decided to sort of cut up the pie. I don't know if it's going to be possible to recruit with that in mind. Like, I don't know if I can.
Yeah, it's smart to.
Yeah. I pose back to you, how would I go about recruiting an individual with a narrow foot versus a wide foot?
You have a narrow foot.
Yeah, fair. I think I would Yeah, rather just recruit everybody and see what happens. And if nobody chooses the narrow skate, and I have a variety of foot shapes, then I know that there's something wrong with how that fit was generated, right? Maybe I need to expand every volume a little bit, and that the narrow fit was too narrow for every single person, even people who have self-proclaimed narrow feet. So I think recruiting from a general hockey playing population is perhaps, I would argue, more valuable.
You mentioned this evaluation comparing like the three fit to the single fit. Did you do the same? I don't know if it'd be possible to compare between like the existing three fit versus this new three fit.
All right, give me a second. It's a hard comparison to make. So, because you're comparing like the existing fits, what CCM currently produces, what was not generated based on this method, was not generated based on 3D foot scans. So the data that I have to compare is not 3D shape of the foot versus 3D shape of the skate versus 3D shape of what I created versus 3D shape of what they already make. It's currently 3D shape of the population, 3D shape of what I created, and then the fit sizing recommendations from CCM. Right, so, and I only have that in those 2D discrete metrics. So if we look at sort of this plot here, I have 4 foot width, skate size on the x-axis, and then that measurement 4 foot width on the y. And the sort of solid lines here with the points represent the TSNE regular, wide, and tapered fits. And then the blue dotted line represents the average shape of the population. And then the green represents one standard deviation above and below. Right, so that within that bound, that covers 68% of the data set. Then we have 2 standard deviations, which is 95% of the data set, right? Sort of like the outer limits. And you can see that the TSNE shapes sort of show up at 1 standard deviation, at least in 4 foot width. So if now I make this plot even messier and add the CCM shapes, we've got the dotted ones, which sort of change the conventions here, but we've got the dotted lines here are the CCM fits. And then in the kind of the transparent ones, we have the population, and then the points represent the TSNE fits. So here you can sort of see that the TSNE fits, what I've created, fall about at 1 standard deviation. And honestly, not too far away from where the CCM regular and wide are, but a little bit sort of narrower bands, if that makes sense. And then the same thing for the narrow fit. And summary here is it's really hard to compare because you've seen a last before, you know that it doesn't necessarily look like a foot, and that's how CCM build their current skates. So they're sort of changing how they make their skates with the information that I'm giving them. So it's sort of like comparing apples to oranges. It's a hard thing to do. It's the best I got.
Do you think that there would be any value in comparing the comfort rating using the current standard versus the new standard?
Yes, but that's not necessarily the goal of my project. That's something that CCM is going to work on internally. But that's a great point as well. That would be sort of a different study design, right? There would be a lot more skate conditions. You just have to elaborate in a different way.
Say, first of all, it was a really good talk. The explanation you gave there about how you did your analysis was super accessible for non-experts and really well communicated. I'm still hanging on something I feel like you said at some point when you were talking about your TSNE foot shapes. You sort of said, I'm using the same terms, but do I understand it then like what you've done is nothing to do with creating narrow, wide, and regular, like you've kind of shaped it, if you're using the words, but it's not simply just a narrow, wide,
Right.
regular
Right.
skate. It's like, it's actually much more complex in terms of its design. Isn't that right?
Yes, so I think you're sort of referring to what I discussed briefly on this slide. The fits that end up resulting from these methods sort of end up looking like a regular tapered and wide. No matter what size we end up feeding it and how big the data set is, as long as it's above 1,000 scans. We sort of end up getting a regular tapered and wide fit that result from that. So the population is sort of naturally segmented that way. But as you saw on those plots I just showed for Jake's question, the regular fit I generated is not necessarily the same as the regular fit that CCM already makes. So this is sort of like a population informed regular tapered and wide. And it might look slightly different to sort of the conventional method, which was take the average foot shape of the population and blow it up a little, and that's your wide fit. And take the average shape of the population and size it down a little bit, and that's your narrow fit. So this is a bit ideally more informed than that.
And maybe just one more quick question that comes to mind when I think about skating, and I think about the I just bought some skates for my 6-year-old, you know, walk around the store. What do you think? Well, it's good, whatever, you know, but then they get on ice.
Yeah.
And they're trying to get this really acute shin angle
Hmm.
and get themselves down. And it's almost like they're walking around the store, their foot's like, their shins vertical and they're walking around, and then they get on ice, and they've got to be in this completely different position to get their shin forward and get pressure in the ice. And I'm just wondering if you can speculate right now, like, how do you think that, sort of touched on it, but how's the difference between how you have to use your positions on ice versus walking? How do you think that's gonna play in? And are there any features here that might facilitate, somebody walks around in the store, I think with a ski boot, it's already kind of inclined that way. And super uncomfortable to walk around in a ski boot, but then you ski and it's like, oh, that's good for skiing.
That's why it's designed that way.
That's why it's designed that way. Do you think that there's like a way with what you've done that it either brings you closer to where your foot needs to be and ankle needs to be to skate well versus being comfortable to take out of the box and walk around?
Right.
Thoughts on that?
I think that's a great point, and I do speculate that we will see differences in comfort ratings on ice versus in-store, replicating that in-store environment. Because we'll ask individuals to try them on, walk around sort of on flat ground, rate the skates, and then they'll skate on ice, do some sprint testings, and then rate the skates again, sort of separately after fact. And I speculate that the skate that fits best in store will not, or that is most comfortable in store, is not most comfortable on ice. And perhaps then jumping from that, their preference in store would not match preference on ice. As far as how I might be able to predict that, that's a hard one, because I have only a singular 3D foot scan. I can only scan an individual's foot, you know, in a position that they're able to replicate barefoot, right? I can't scan their foot while it's inside the skate. So perhaps like a little rig where you could sort of set up the pitch of a hockey skate, because those are sort of pitched in the same way that ski boots are, might be valuable. But yeah, it's an interesting question, on ice versus in store, and which one should you be selecting for? I don't know.
I agree with that. It's a great presentation. It's very clear and accessible. I don't pretend I understood everything. So what I got lost is when you validated your model. So did you validate it to the actual scans, to the actual model that is created from the scans of each individual, and then we calculated how much the difference in fits like between the model and the actual one? How did you exactly validate?
Sure. So I think the best slide I have to potentially explain this would be that the model, the fits were generated in order to evaluate the success. The fits were generated from a training data set. So imagine this validation data set as way off to the side. The fits, 3 fits, and then separately a single fit were generated from a training data set and then compared back to a brand new population of validation data set, a test data set. And I did that using this sort of 3D fit metric called deviation. And then resulted in an improvement when compared to sort of that new calculation.
So you calculate the deviation at the various points and then you calculate the mean.
Yes, exactly. So if you can imagine, sort of like if 0.1 on each scan is big toe, and 0.1 here is on blue, and then 0.1 is here on red. Calculate the 3D distance. So imagine a vector from one to the other. In 3D space, calculate the length of that vector. And that's the Euclidean distance between the two. So you sum that up for all of the 5,000 points in this scan. And you take the average of that, and that becomes the mean deviation metric.
If one region is more deviated than the other, it will affect your average. So-
Yeah, yes. So, like, for example, here we can see that the big toe or the toe region doesn't fit very well, at least in the way that this is aligned. So that would affect the average overall. And some regions of the foot in this representation might fit really well and some might not. And I think possibly what you might be alluding to is, should I be calculating fit this deviation region by region? And we've thought about that. I've kind of gone down that rabbit hole, but it becomes pretty abstract at that point. How do you determine which region is most important and not? I have a feeling I'm going to apply that sort of analysis. I get the validation, or when I get that real population coming in and testing them on ice and seeing how they sort of rate the comfort of the foot. Maybe like an individual who says the forefoot in this skate fits really bad shows up like this. Like, that would be pretty cool if I could replicate what an individual is telling me in 3D space like this. That would be pretty neat and sort of predict that. So yeah.
I just wanted to get some clarification about how you're using your measures. So as I understand it, one of your measures is a ranking of preferences between four things, right?
Yes.
Regular, skate, and the three that you're using.
To clarify, no, they will not be ranking their own skate.
Okay, only in between.
Correct. Yeah.
And you're also measuring comfort
Correct.
with some survey
Correct.
and performance. So how are you using these different things?
How will what will my analysis method be?
Well, I guess what's clearest to me is you're gonna use the preference and you have an idea that ideally the preference will line up with what you intend with your predefined shapes, right?
Right.
But then.
Sort of this plot.
Comfort and performance into whatever outcome.
Right. So I only presented expected results. You're right, for the first sort of primary research question, which is just best fit and preference. Best fit being the mean deviation. I think the way I would compare or add comfort into the mix, I'm going to use sort of visual analog scales to say, like, how comfortable was this from least comfortable to most comfortable at all time, sort of thing. An individual will mark overall, and then for specific regions of the foot, from there you can sort of obtain an overall comfort score out of a certain value. And then I can see if that's correlated with their performance and potentially their mean deviation metric as well. But then comparing to the categorical data of the fit preference is challenging, and I don't know if I know necessarily how that looks yet.
I think I want to return to the question of the three existing shapes. I kind of want to advocate for it, including because even within rankings, it's not clear whether you improved on anything. You know, I could come say I designed 3 new skates. They happen to all be different kinds of Birkenstocks. I can rank them. I have a favorite Birkenstock and etc. But they're not necessarily improvement over what CCM already uses. So I just feel like both for the question of comfort and for even the ranking preferences, if you're ranking 6 skates, say, then you have an idea where you sit relative to the existing ones there.
Yeah.
10 is just more data. And,
Yeah.
you know, I'm recognizing, you said that it's not the same kind of data because
for your shapes, you have foot scans, and then you don't have an equivalent thing for the CCM. But the idea still is that you want to see where you are, relative to the state of the art.
Yeah. So you're right, with this current study design, I can't make the statement that my fits improve on any current methods, because I'm not actually comparing in this, as I've outlined, to the CCM skates. I worry that adding those skates into the mix, call them the current CCM tapered, regular and wide, would add a lot of length to my study visit. That's then 6 skate conditions plus a test retest reliability condition at the end that you have to go and test. People get tired of lacing skates on and off, and so I think that was my justification for not including them. And then, like I said earlier with Jake's question, I think that's a question CCM will try to answer themselves, because they will also have these skate models and they'll perform the testing sort of in-house to see whether it's an improvement over current.
Okay, and then I'd also like to turn to Bill's comment earlier, and you said CCM wants the skate to fit out of the box. And what I would suggest is take skates after they've been worn for a while, and after they've been molded, and I believe that with heat molding, they also continue to mold themselves to the foot, even after they've been heated in oven to sort of continued use. Take molds of those skates, do your analysis on that, and now you know the dimensions in which skates actually vary, which presumably is mostly due to the on-purpose molding and whatever adaptations occurred since then. And now you know at least, what are the pieces of the shape that are getting blown out.
Right.
And then that might form, if you can sort of do some of that in the basic shape, then maybe there's less molding needed, better on the box fit. So it's basically using your method, not on the people, but on the skates.
Right. Yeah, that's a cool suggestion. And that would require adding something in that we don't already have, which is taking molds, skates. Yeah, I'm curious how much use it would take for a skate to start to fit the foot of the person that's wearing it.
Well, I think that one is the hard one, but if you're just talking about when they go back to the store for the molding, I believe that a large percentage of those are just things like the malleolus of the ankle is,
Pinching.
bothering somebody and they're asking for that to be blown out. I bet you it's a relatively finite number of changes that people ask.
Right. And yeah, probably more popular asks than others as well. That might be beyond the scope of this study. I think that would be a really interesting study as well. But it's sort of beyond what I think I have time for. You're looking for a, yeah.
Question is.
Well, then I agree, yeah. I agree. No, that, because I think footwear does change over time and overuse, and I think, yeah. Optimizing that is interesting.
So I don't really skate too much, but I do have flat feet. So I just wanted to ask if skates, like, just out of curiosity, do skates account for flat feet? And if so, like when you're doing with modeling, do you look at flat feet as a part of like the actual foot shape within the skate?
First part of your question, mostly what I'm looking at is sort of the upper of the skate. So I would say that the skates generally come with like a little bit of an arch, like most footwear normally does, right? It normally has a little bit of sort of curvature to it, but they don't necessarily come with immense arch support. What I'm trying to get CCM to sort of revise and reinvent is the upper material. I'm not necessarily looking at what's underfoot. I think that's a separate topic. I think that's insole work rather than skate upper work. But that's an interesting question too, because that, what's underfoot plays into somebody's comfort in a totally different way, right, than what's on top of their foot. And the combination of the two is important as well. So I don't necessarily have skates for you because you have flat feet, but we'll see.
So does the triangle with performance comfort translate into prevention of injury as well?
I do not want to make a statement on it. But it could, and there's several hockey specific injuries, hockey skate specific injuries that you might have heard of. There's bunions that frequently occur in hockey players and skiers. And then there's actually a condition colloquially called Bower bump, which is like a heel spur. And I'm not sure exactly how it works, but it's sort of like friction and a combination of friction and pressure right on the heel that causes sort of a bony deformity right on the heel, kind of like a heel spur, I think. And you could make the argument that those come from improperly fitting skates. So if you can improve the fit of skates, maybe you can reduce the occurrence of those injuries. That's the statement I might be able to make there.
Question going back to the data collection. I'm just wondering, like for the comfort preference, you're saying you're gonna rank them from like kind of like most comfortable to most comfortable. Sorry, not, well, about like I think like, I was just wondering how you could limit subjectivity when participants are answering it, because I think everyone might have a different opinion on what is like more comfortable than another one.
Yeah.
Like just when it comes to, I think like just that comfort aspect.
Yeah, I see what you're saying, like, everybody's gonna have their own preferences, but I want to know that, right? Because that's how an individual will go and buy skates. And it's maybe not the most scientific question to think about, but CCM as a business, they want people to buy their skates. And so we want to know how people select those. When they try on multiple fits, we want to know maybe what sort of measures correlate well with their eventual selection. So maybe it's fit at the toe that's really, really important or really well correlated with which skate they end up selecting. And fit at the ankle doesn't matter as much, or maybe it's the opposite of that. So I'm going to collect comfort overall, like how do you rate the comfort of that shoe? And I'm also going to collect comfort of specific regions of the foot, and maybe that'll help me sort of pick up on patterns.
Question. I'm just curious on your secondary research questions, like for the on-ice performance, do you anticipate in the future, like how you're gonna do the on-ice performance? Like it's gonna be like an actual competitive game or like a game where it's just like a simulation, you know, or is it gonna be a real game where you have different skates on?
It would be, it would be really cool to go to that level of performance. But what I've got for performance is admittedly quite simple, and it's just sprint performance times. So individuals will try on each skate on ice and sort of get a feeling, get warmed up, and then skate this distance, about 16 meters twice in each skate. We'll take the times that they take to skate that distance, and we'll call that our performance metric. There's other ways to quantify performance, and skating is obviously a lot more complicated, and hockey in general is obviously a lot more complicated than just skating in a straight line as fast as you can. But that's sort of what I'm capping it at for the sake of finishing this study soonish.
Thank you for your presentation. I really enjoyed that. I have one quick data question and then a study design question. CCM sells half sizes. So what happened to all the half size data?
They are making half sizes based on the grouping of individuals they're basically making half sizes based on the full sizes and expanding them a little bit. That's what I've been told.
So did you round up your data or round down, or you don't know? They just.
My size 7 data was the size 7 and the size 7.5 buckets.
Okay.
And so I took the average shape for that, and that's what ended up being the suggestion to the client.
And then my other question is, so you've got sizes 4 to 10. And if anecdotally it's mostly boys and men, then most of your data are from preteen boys and teenage boys.
Yep.
So if you assume a 10-year-old's around a size 4, 12-year-old's a size 6. So that size 6 foot that you found is mostly from preteen or teenage boys. Yet you're gonna test it in adults, who will mostly be adult women fitting into that size. So what are the implications of designing footwear based on a growing body and testing it in a different sex?
So I should have clarified this earlier, but skate size, which is covered here, is different than like US sizing. So I'm a size 11 in US men's normal footwear, but I'd be a size 9 in skates. So you can sort of think of an offset. And like this is the general adult population from size 7-ish up to size 11 or so. And that's why we have most of our individuals in this region. The intermediate skate sizes are 4 to 6. So that's sort of the teenage range. And then the adult range is size 7 and up. So we actually do have a mostly adult population in the data set,
Okay, but not for size 6.
but not for size 6. Yeah, that's a good point. Okay, I see what you're getting at. So,
like my
right,
9-year-old
yeah,
daughter is wearing a size 4 skate.
Yeah.
Right now, which is probably bigger than others, but yeah, so, but you will be testing that size 6 probably in females.
that's a good point. Okay, so yeah, the females that come in will be on the lower end of my size spectrum. That's interesting. And that is we'll probably see pretty bad fit there. And I think that will probably, I hope that proves to us that we need to apply these types of methods to a female specific population. Like we need to gather female foot shape and turn those into skates rather than using preteen boy foot shape to inform female skate development.
Or if you could get REV to bring in some youth as well, you'd be able to confirm that.
Yeah. Right now I have it at 18 plus, I think, to save some time and effort, but
Yeah.
it's a good suggestion.
Opening up a feature. project.
That is, yeah. And I think this is important in the youth sizes as well, which you can sort of see is, I've got less data on, but could be applied, same methods could be applied there too.
All right, well, thank you again.